Alright, we're looking at 6.1, problem number 7. We're using revolutions of solids and integration in order to find the volume of a symmetrical figure in this case. So what this gives us is it says, find the volume of the solid generated by revolving the following regions about the given axis. It says the region in the first quadrant, so here's the first quadrant, that's bounded above by y equals x squared, that's this graph, and on the right by the line x equals 1, and it's rotated about the line x equals minus 4, which is way over here, right? So it's not centered about the origin where we're rotating. But we do know that we're looking for, in other words, the area that's in here, and we're going to revolve the whole figure around. There's going to be kind of a donut. There will be part in the center where there's a hole, and there will be flanged edges. But we don't need to worry about the overall shape. All we need to do is look at the smallest and most arbitrary piece, for lack of a better word. In other words, when we're doing calculus, the most important thing to remember is that you need to figure out a pattern that works for every single component. And so what I mean by that is this has asked us to do the washer method, which means that we're going to integrate with respect to dy, and we're going to take these dy by some length. We're going to rotate them around the x equals minus 4 line. And for each one of these, you're going to end up with a washer. But it's important to keep in mind that there are infinitely many of these washers that we're stacking up. And so it's important that when we write an equation for our general washer, that it matches every point on the integration, right? We're going to integrate washers, 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 up to there, and it'll find us the volume. So I always like to draw out my washer. In this case, we know that the width of the washer is our little infinitesimal dy, so that's our height of the washer. And with a washer, there's two radii. There's our first radii, or our inner radii, and our outer radii. And so the first thing I'm going to do is I'm going to solve for R2 and R1 in terms of our graph. So if I'm looking for R2 equals, well, I know that R2 is my widest radius, right? And in this case, the furthest point I can go to is x equals 1, because I'm bounded on the right by x equals 1. So my outer radius for every one of these washers is actually constant. So what I have is I have my 1 minus my minus 4, which is where the axis is at. And what you'll find is that radius 2 is always 5. So in other words, from here to there is always 5. 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 It works for every component in my integration. Now how about radius 1? Now radius 1 changes, right? Radius 1 for this bottom part is here. And then it follows this graph up until the integration ends. And it's actually based on the x value, right? Wherever our x value for our graph is, that's where we're interested in, right? If I look at this right here, this particular rectangle, you'll notice that it is in fact it's x away from the origin, right? And I know that from my origin over to my rotation, I know that that's minus 4. So what you'll notice here is if I want to figure out my distance to the inner radius, I'll take minus 4, or I'm sorry, I'll take 4, because that's a positive, well, no, we'll do it this way. So we're going to take x, because we know that we're x out, and then we're going to subtract minus 4 again. And that's going to give us x plus 4. And that makes sense, right? Because we know that from the revolution's axis to the origin is 4. And from the origin to wherever we're at is going to be a distance x, according to the function. And so now that we have R1 and R2, we're going to go ahead and erase this nice picture and set up the integral. Alright, So another important thing is to find our boundaries. We're integrating washers from here all the way up to here. And at the very top, we're curious of how high that is. Because we're integrating with respect to y. That's why we're using an infinitesimal y. So it's important to find everything in terms of y. And so if I were to plug in f of 1 to my function, I would end up with 1. And that tells me that I'm integrating up to y equals 1. And I'm starting down at y equals 0. So I'm integrating from y equals 0 all the way up to y equals 1. So that'll be my boundary. Well, now I'm interested in my little chunk of volume. And I'm a little disappointed that I erased the picture, but you remember that there was an inner radius and an outer radius. So the outer radius, pi r2 squared minus the inner radius, pi r1 squared. What we're doing there is we're taking the area of the big circle and we're subtracting the area of the little circle, which gives us the area of our washer. Well, then the only thing we need to do to make it a volume is we need to multiply by the height, which we know is an infinitesimal y. So this is our small infinitesimal chunk of volume is equal to the outer circle minus the inner circle times the width of the washer. Alright, so now let's start plugging things in and we'll start writing our integral out. We know that we're going from y equals 0 to 1. We know that everything's being multiplied by pi. And so we can write this as pi times r2 squared minus r1 squared. And we're integrating with respect to y. I just factored a pi out of both of those. And so now at this point we're going to plug in what r1 and r2 are worth, what they're equal to. So we're going from 0 to 1 of pi times r2 squared, 5 squared, is 25, minus r1 squared is x plus 4 quantity squared. And we're integrating with respect to y. So now what we're going to do is we're going to factor this out, the x plus 4 squared. And what we'll end up with is 25 minus x squared plus 8x plus 16. All of that's still integrated with respect to y and all multiplied by pi, going from 0 to 1. And now we're going to go ahead and simplify by distributing our minus sign into all these terms. So to do that, the x becomes a minus, the x squared becomes a minus, the 8x becomes a minus, and the 16 becomes a minus. And then we can simplify. 25 minus 16 is 9, positive 9. And so now we're further simplified. And then at this point, remember we're integrating with respect to y. We have a bunch of x's in here, and we don't want those because we're integrating with respect to y. So we need to figure out if y equals x squared, what does x equal? Well, x equals, if we take the square root of both sides, x equals the square root of y. So then we'll take this identity and plug it in for all of our x's. So I'll write the finished product up here. Hopefully I have enough room. We're going from 0 to 1 of pi times 9 minus x squared, but x is root y. So root y squared would just be minus y. Yeah, just think about that. If we plug in y here, or root y for x, root y squared is y. So we're subtracting y. And then we're subtracting 8 times y, 8 times x. And x is equal to root y. So we'll just plug in root y there. And we're integrating with respect to y. And so that is our setup. Let's see if it's right. 9 minus y minus 8 root y from 0 to 1 with respect to y. And this is the setup. And at this point, the only part left is to take the antiderivative and plug in the boundaries. The hardest part of these problems is setting them up. So I hope this was helpful, and I'll see you next video.